Few people realize it, but astronomy is undergoing a silent turning point. Instead of simply confirming old theories, the James Webb Space Telescope has begun to dismantle seemingly solid boundaries. In just a few years, it has revealed improbable planets, atmospheres that shouldn't hold up, galaxies too young to exist, and chemical signals that unsettlingly challenge the idea of life beyond Earth. And this isn't limited to a single case like K2-18b. Discovery after discovery, a larger picture is emerging. The universe is stranger, more active, and more inventive than any model predicted. What once seemed like mere speculation is now being seen. One of the first shocks comes from a world that, in theory, shouldn't function. TOI 4507b is similar in size to Jupiter, but absurdly light, inflated like a balloon that should have already collapsed. Even stranger is its path. It rotates almost sideways relative to the star, in a nearly perpendicular orbit, something that points to a violent past, full of gravitational shocks. Even so, it is too far from the star for heat to explain this swelling. Webb is now studying its atmosphere to understand how such a large planet can be so light. And this case alone shows that our equations about planetary evolution are incomplete. And it doesn't stop there. When the telescope looked at the young universe, it found something even more disturbing. Supermassive black holes already fully formed and active just 500 to 570 million years after the Big Bang. Too early to fit into current theories. Objects like those found in galaxies such as LRDZ9 from the Ceres survey and LRD8 from the Canucks project have masses hundreds of millions of times greater than that of our Sun. According to standard cosmology, there simply hasn't been enough time for black holes to grow that large through conventional processes. These discoveries suggest that black holes can form directly from the collapse of giant gas clouds, bypassing the slow and gradual growth that we previously believed to be mandatory. In other words, Webb is showing us that the universe learned to build giants almost immediately. And, if that's true, then much of what we thought we knew about cosmic evolution needs to be rewritten. Webb's revelations continue closer to home. With worlds so extreme they seem almost fictional. Meet WASP-18b. An ultra-hot gas giant that orbits its star so closely that its atmosphere reaches temperatures where water literally boils and instantly turns to steam. Using advanced spectroscopy during planetary eclipses, Webb achieved something never done before, a three-dimensional map of an exoplanet's atmosphere. What it revealed was stunning. Supersonic winds tearing across the planet, redistributing heat from the scorching day side to the night side, creating one of the most complex atmospheric systems ever observed. This is more than just a curiosity. It represents the beginning of a new era in which alien atmospheres can be modeled in detail, not just imagined. And Webb didn't stop there. He also detected a dense atmosphere around TOI 561b, a super-Earth orbiting extremely close to its star. According to previous models, such a planet should have lost its atmosphere long ago. However, it hasn't. This single observation forces scientists to reconsider how resilient planetary atmospheres can be, even in environments previously considered completely hostile. Perhaps the most disturbing discoveries come from Webb's observations of the early universe itself. The telescope identified a spiral galaxy, already well-structured and mature, existing only 100 million years after the Big Bang. This should be impossible. Galaxies should take much longer to form such organized shapes. Either the universe began earlier than we think, or there is an unknown mechanism that dramatically accelerates the formation of cosmic structures. And then came the discovery of the oldest supernova ever associated with a gamma-ray burst, exploding just 730 million years after the Big Bang, scattering the first heavy elements into space. These elements are essential for planets, for chemistry, and eventually, for life. Webb isn't just showing us distant objects, he is showing us that the universe has become much more complex than we ever imagined, and this finding sets the stage for something even bigger. As the James Webb continued to advance through hostile environments, it began to discover planets that simply shouldn't be able to exist in their current state. Around neutron stars and pulsars, objects once considered completely sterile, Webb and complementary observatories have confirmed planets that somehow survived the violent supernova explosions that created these remnants. These worlds withstood bursts of radiation capable of shattering atoms, shock waves that should have expelled any nearby material, and gravitational chaos that normally destroys planetary systems, and yet they remain. More unsettling, some of these planets appear to retain atmospheres or surface materials that indicate long-term stability. This forces astronomers to confront an uncomfortable truth. Planetary resilience is far greater than we ever allowed in our models. If planets can survive the death of a star, then the line between habitable and uninhabitable environments becomes much more blurred than our models ever suggested. One of the most disruptive discoveries made possible by Webb is the growing list of exoplanets that maintain thick atmospheres under conditions where atmospheric loss should be inevitable. Super-Earths orbiting extremely close to their stars, bathed in intense radiation, should have been reduced to bare rock. Instead, Webb detected atmospheres rich in heavy molecules, suggesting powerful mechanisms for continuous retention or replenishment from the planet's interiors. This implies that planets are not passive victims of their stars, but active systems capable of maintaining equilibrium for much longer than previously expected. Volcanism, magnetic fields, and large internal gas reservoirs may play a much larger role in planetary survival than previously believed. The implication is striking. Planets previously dismissed as dead worlds may still possess dynamic and evolving environments beneath their hostile surfaces. Webb's spectroscopic power has revealed chemical combinations in the atmospheres of exoplanets that should not coexist for long periods of time. Methane appearing alongside carbon dioxide, sulfur compounds persisting under extreme heat, and water vapor surviving intense stellar radiation point to active chemical cycles, not static compositions. In equilibrium, these molecules should destroy each other or transform rapidly. Their persistence implies constant replenishment or regulation, processes that keep the atmospheres chemically out of equilibrium. This is a crucial point because chemical imbalance is one of the strongest indicators of dynamic systems. While this doesn't mean life, it does mean activity. It means planets that are not chemically frozen, but constantly evolving, reacting, and reshaping themselves in ways that go far beyond our previous assumptions. Taken together, these discoveries are beginning to erode the traditional concept of the habitable zone. For decades, habitability has been narrowly defined, a thin ring around a star where liquid water could exist on the surface of a planet. Webb is showing us that this model is far too limited. Worlds outside this zone retain atmospheres. Worlds within it may be far more extreme than expected. And worlds once considered completely hostile may still sustain complex chemistry. Habitability, it seems, may not be a place, but a spectrum, a sliding scale of conditions in which chemistry, energy, and time interact in ways we are only beginning to understand. And if that's true, then the number of potentially interesting worlds in our galaxy doesn't just increase a little, it explodes. As the James Webb Space Telescope continued dissecting exoplanet atmospheres molecule by molecule, scientists began to notice something that quietly sounded the alarm. Certain planets were exhibiting chemical combinations that shouldn't persist unless something was actively maintaining those conditions. In stable situations, gases like methane and carbon dioxide destroy each other on relatively short timescales. They react, transform, and disappear. And yet, Webb continued to find these gases together, coexisting in atmospheres exposed to intense radiation and stellar winds. This is not a statistical anomaly. It is a sign of chemical imbalance, a state in which inputs and outputs are constantly being balanced by an active process. The most important thing is that this doesn't automatically mean life. Volcanoes, photochemistry, and deep reactions within planets can also generate chemical imbalances. But the main finding is this: these planets are not chemically dead. They are dynamic systems, constantly processing energy and matter in ways that defy long-held assumptions about atmospheric stability. Even more unsettling is where some of this chemical activity appears to be coming from. Several exoplanets observed by Webb receive far less stellar energy than would normally be needed to sustain such complex atmospheric behavior. In other words, the star alone cannot explain what we are seeing. This forces scientists to consider internal energy sources on a much larger scale than previously imagined. Tidal heating, radioactive decay, and deep mantle chemistry are suddenly shifting from secondary factors to central protagonists. Entire planets may be operating with internal engines, slowly releasing heat and material over billions of years. This radically expands the number of worlds that can remain active long after their stars begin to weaken. This also suggests that planetary evolution is far more independent of stellar evolution than our models ever allowed. At this point, a dangerous temptation arises: to label these signals as evidence of life. And this is where the scientific community becomes extremely cautious. Webb did not detect life. What it detected were conditions that resemble environments where life could exist, without proving that it does exist. This distinction is crucial. False positives have plagued astronomy before, from channels on Mars to misinterpreted spectral lines. Now scientists face a paradox. The data is richer than ever, but so is the risk of overinterpretation. Every possible biosignal must be tested against dozens of non-biological explanations. And yet, the uncomfortable truth remains: if life exists elsewhere, this is exactly what the earliest signs would look like. Subtle, ambiguous, chemically suggestive, but never definitive on their own. At this point, one thing became unmistakably clear: the universe does not respect the clean categories we have constructed for it. Planets are not simply dead or alive, habitable or hostile. Atmospheres are not simply stable or non-existent. Galaxies do not always form slowly. Black holes don't always grow patiently, and chemistry doesn't wait for perfect conditions. The James Webb Space Telescope is showing us an opportunistic, fast-paced, and incredibly efficient universe at creating complexity whenever energy and time meet. This doesn't mean the cosmos is teeming with life, but it does mean that the basic processes that lead to life are far more common than we ever dared to suppose. And this realization fundamentally changes what it means to look for answers in the sky. At this stage, the most unsettling realization is not any single discovery, but the pattern that emerges when they are all placed side by side. James Webb isn't finding a strange planet or a bizarre atmosphere. It's finding the same types of anomalies repeating themselves in completely different star systems, on different types of planets, and in radically diverse environments. Hot worlds, cold worlds, gas giants, super-Earths, planets around calm stars and planets around violent stars, all showing signs of unexpected complexity. Atmospheres that refuse to collapse, chemistry that refuses to balance, internal energy sources that keep planets active long after the time they should have become silent. This repetition is crucial because randomness doesn't repeat itself with such consistency. Patterns imply underlying rules, and those rules aren't the ones we've used for decades. Webb is quietly telling us that complexity is not an exception in the universe. It is the default outcome whenever matter, energy, and time have enough room to interact. As these patterns have become clearer, the scientific community has done something unusual. Instead of rushing into dramatic statements, she slowed down, carefully, deliberately. Because everyone involved understands what's at stake. The chemical signatures that Webb is detecting come dangerously close to what we would expect from biological processes. But expectation is not evidence. Methane alongside carbon dioxide, long-lasting imbalance, internal energy driving surface, and atmospheric renewal. All of this can be produced by non-biological mechanisms under the right conditions. And yet, that's precisely why the moment is so tense. For the first time, astronomy is touching a frontier where the data are no longer comfortably abstract. They are suggestive, ambiguous, provocative. Webb isn't shouting life, but whispering something far more unsettling. The universe continues to build environments where life wouldn't be surprising. And that's a very different statement. For decades, the search for life beyond Earth has followed a narrow path. Finding Earth-like planets around Sun-like stars at the right distance with the right temperature. The James Webb Space Telescope has destroyed that strategy. What it is revealing instead is a universe where the potential is not concentrated in rare, perfect conditions, but spread across a wide spectrum of worlds. Planets that are too hot still maintain active chemistry. Planets that are too cold still generate energy. Planets that should have been completely stripped of their atmosphere somehow manage to retain thick atmospheres. The implication is striking. The question is no longer how many Earths are out there, but how many paths to complexity exist. And when you ask that question, numbers cease to be comfortable. They grow very, very fast. When all these discoveries are considered together, the word unimaginable takes on a very precise meaning. It doesn't mean aliens, civilizations, or definitive proof of life. She means that the universe is operating at a level of creative efficiency that we never took into account. The James Webb is showing us that planets don't need ideal conditions to become interesting, that chemistry doesn't need mild environments to become complex, and that time doesn't need billions of tranquil years to produce structure. The unimaginable thing is not that life exists elsewhere. What is unimaginable is that the universe seems almost designed to try again and again in places we dismiss, under conditions we exclude, with mechanisms we are only now beginning to understand. And, at this point, the data leaves us with an inescapable conclusion. We are no longer asking whether the universe can produce complexity. We are seeing this happen in real time throughout the galaxy. So where does this leave us? After following the James Webb discoveries through planets, atmospheres, galaxies, and chemical systems that refuse to behave as they should, one truth becomes impossible to ignore. The universe is not cautious. He doesn't wait for perfect conditions. He doesn't limit complexity to narrow zones or rare worlds. He experiments everywhere, tirelessly. And what Webb revealed isn't a single shocking discovery, but a new pattern that forces us to rethink how reality itself works. For years, we've shaped the search for meaning in the cosmos around a simple question. Is there life out there? James Webb is quietly telling us that this question may have been too small. What we are seeing instead is a universe full of active chemistry, persistent sources of energy, resilient atmospheres, and worlds that refuse to become inert. Even when conditions seem hostile, complexity finds a way to survive, adapt, and continue evolving. This does not mean that life is everywhere. This suggests that the path to life is broader, more flexible, and more frequent than we ever accepted. That's why this moment is so unsettling. Because when you take seriously what Webb is showing, the silence of the cosmos ceases to seem empty. It starts to sound like weight. The question is no longer whether the universe can generate extraordinary things, but how many of them we miss, because we're looking at them the wrong way. The James Webb Institute didn't deliver final answers. It did something bigger. It forced science to face the fact that the unimaginable isn't a distant tomorrow. It's already underway. And, as Webb continues observing and new missions expand on what it has revealed, it's becoming clear that the universe we thought we understood is a thing of the past. In its place, emerges something far more active, more inventive, and full of possibilities than we dared to imagine.